I also realized that I have a single marker here today that works. It's my purple one. I'll pick some more up today because normally I do with more colors. But we've been talking about waves, and when we've been talking about waves, we've talked about the wavelength. That's measured in meters. We've talked about the frequency. That's measured in hertz. And we've talked about wave speed. Measured in meters per second, or velocity. We talked about it in both ways. And so that's kind of been our general stuff that we started on before break. And the idea of a wave is that it's energy that's passing through a medium. It doesn't take that medium with it, but it disturbs the medium and allows that energy to go through. And we had two types of waves that we were looking at. We were looking at transverse waves. And transverse waves are the ones that go up and down like this. And so they're the ones that what happens, the way that we talk about that in a physics standpoint is we say that that the motion of the medium, the disturbance of the medium is perpendicular to the motion of the wave. So the wave would be traveling that way, and we would see the medium going up and down like this. The other type of wave that we have is called a longitudinal wave or compression wave. And what happens with a wave like this, the disturbance of the medium is parallel to the motion of the wave. So if the wave is going that way, the medium actually goes back and forth like this. And so, let me grab my slinky here. This is a fancy giant slinky. Let me take this out of the way so you can see it a little better. And so if I take this and put it on here, normally I would do this like we'd all traipse out to the hallway and you'd all have to stand really close. We're not going to do that. But if I take and I send this back and forth here, get a little bit better of a grip. You can see where it gets tight and loose. And so if I get this tight and loose here, you can see that going back and forth. And what's happening here is it's areas that are compressed and then areas that are released. And while I just had that going in one spot, that's how a compression wave is going to travel. So when we talk about longitudinal waves, we end up having something that is really, really tight, and then loose, and then tight, and then loose, and it would continue on like that. We don't usually draw these waves. In fact, if we're talking about this type of wave in a way that needs drawing, we frequently still draw it as a transverse wave because that's what makes sense to what a wave can actually be measured as and calculate. And so as we're going through and doing this, we want to take and kind of keep in mind that even if so with sound is always going to be a longitudinal wave. Sound works because of the way that your ear picks up the vibrations in the air. And so when I speak, it radiates out through the entire medium. And it goes, your eardrum is really sensitive and picks up the differences in the way that the air is vibrating. If we took all of the air out of the room and didn't have any medium for it to travel through, sound wouldn't work. You couldn't breathe either, that wouldn't work. There's lots of things that wouldn't work there, but sound wouldn't work. Light kind of creates its own medium. That's a different thing, and we'll talk about that later. But if you're out in space and something explodes, you cannot hear it because there's no way for that energy to be propagated through the vacuum of space. So sound, when we start talking about sound, there's a couple things that we have to know. First of all, sound has to have a medium for it to travel through. Right now, that's air. That's the environment around us. If you are underwater, you can hear sound come through underwater. If you put your ear against the table and knock on the table, you can hear that be propagated through the surface of the table. So the medium can be just about anything as long as it's something. It has to be something. And so sound travels throughout all of it at the same time. So let me grab one thing. So have you seen these air puffers before? Okay, I love these things because they're fun. So what they do is I can shoot air wherever I can shoot the air. And so Taurus is coming at you, so just kind of be ready. We'll see if it gets there. Oh, yeah. Okay, we'll try it again. Yeah, okay. So you can see that you hear it snap, and you hear the air be shot out, but you don't necessarily see it until it's traveled a little bit. There's been a gap in time there, and then you see that puff of the air. And so what happens with this is the sound travels out throughout the air, and everyone hears that at the same time. For the most part, we're close enough. However, if it were to take the air with it, then the only way you would hear it is if that puff of air hit you. So we like that sound travels in this way because then otherwise I'd have to look directly at each person and say the same thing over and over and over again. That would get a bit repetitive. So sound travels through the air, it does not take the air with it. Here I shot a puff of air, different deal. So you can see the difference between those two. Sound also, we have a range of hearing. And the human ear can hear from 20 hertz to 20,000 hertz. So in ideal circumstances, the human ear can hear in the range of 20 hertz to 20,000 hertz. And what happens with that, so when somebody's born and their ears are absolutely perfect, 20 hertz to 20,000 hertz. As time goes on, and if you take anatomy and physiology, they'll get into all of the kind of workings of the inside of your ear and how all that works. But as time goes on, if that starts to deteriorate, it's these ends that start to move in. Now you might be thinking, I'll do a demonstration of that in a moment. You might be thinking like, I don't care, I don't need to hear the 20,000 hertz. Fair enough, it's a pretty obnoxious sound. However, as this starts to go in, then other kind of parts of hearing start to be affected as well. So I just want to show you what that looks like. I have a speaker here. I'm going to go all the way down to go real low. That didn't work. Hold on. There we go. So a speaker works by essentially, like when I had the Slinky and I was pushing it back and forth like that, essentially that's how a speaker works in the way of air. So when I turn this on, the speaker, if it goes, no, come on little speaker, I need you to work today. There we go. So as this is moving in and out, you may or may not be able to see it, but as it's moving in and out, I have it set at 1 hertz right now. So 1 time per second it's going in and out. If I take and I move this up, I'm going to just slowly move up. I'm going to go to 5 hertz. You can see that the ball is bouncing up and down a little bit. If you're looking right at that, let me move it over here. Let me see if it's visible there. So the ball, you can see, is bouncing up and down. You can't hear the sound of it yet. If I go on up, okay, I'm at 10 hertz. The ball just bounced out. And so the speaker's going up 10 times every second. Well, again, our ear cannot hear that sound. However, as we get farther along and as we get to 20 and above, our ears should start to be able to hear it. So you can see kind of that bouncing around there. We'll try and keep it from bouncing out. I'm going to go up to 20 hertz. You may or may not be able to hear it. You hear a low hum. Maybe. If I put the ball on here, you can see it bouncing around pretty quickly. It's moving 20 times every second. Usually by about 50 hertz, 40, 50 hertz, people start to hear it, so I'm going to move there. We're at 40 hertz, sort of a low buzz. 50 hertz. Let's see if I can get that out that way. I'm going to jump up to 100 hertz. These are all pretty standard sounds that we hear. If you are into music, I'll talk about music more on Tuesday and how we do resonance. Specific notes have specific frequencies that are tied to them, and then kind of in the way that we hear the music. So at about 160, 200 hertz. Let me take it off so it's not resonating. So it's a hum here. I'll just hold it like this. Okay, 200 hertz, but now I'm going to go ahead and I'm going to start jumping up higher. 500 hertz. Again, nowhere near 20,000. So I'm going to go up by hundreds now. 1,000 hertz. 5,000 hertz. Not the best thing in the world. Nobody wants to listen to that too long. I'm going to go ahead and mute this. I'm going to go up to 20,000. And then I'm going to start bringing it down. Now here's what will happen. Usually what happens is that I am older than you all, obviously. I can't hear the same range that you can. So what'll happen is you'll be like, oh, it sounds terrible. And I'll be like, don't know. But also keep in mind that like I rarely had stuff in my ears, so earbuds weren't a thing. We all had like big old things, and they didn't even go that loud. So I'd say like my age group generally will have, I'll just say this, I'm concerned about all of your ears at some point, just for the amount of going around with those that can be happening. So it's just over time, if you want to go into something that's going to make you a lot of money someday, go into like hearing systems because I'd say my age group too, but I'd say even more so this current age group is going to need them. So let's go up to 20,000. Go up to 20,000. Most people aren't going to be able to hear 20,000. I'm going to go down by tens. Okay, so this is going to be obnoxious. When you can hear it, just put your hand up and take it down. Make sure we can. All right. I'm going to get down to 19,000 here. Anybody hear it at 19,000? Yeah, a little bit? So you've got good solid strong ears right now. I'll go down to 18,500. It's obnoxious, isn't it? Anything? Good. You catch it? I'll move it back and forth a little bit. Okay, we're at 18,000 right there. Thing is, I can't hear any of it. 17.5. Yeah, I'm starting to get there. I know, it's terrible. 17,000. I'll turn the volume down. Again, I can't hear it still. Down to 16,000. Nothing up here. Go down to 15,000. I won't continue doing this to you. Yeah? 14. Go down to 10. Now it's going down. We'll stop that. Okay. So over time, that changes as you go with it. When cell phones were kind of early 2000s, they made ringers on them that you could only hear if you could hear that really high upper range. So they marketed them that adults couldn't hear them, and that was true. Like we did it when we were. It was probably about 2010. 2012, somewhere in there, and we did it in class, and I'm like, all right, pull them out, let's see. And so we measured them and stuff, and yep, people couldn't hear them. Kids could, adults couldn't. A few years ago, that light back there, that middle light in the back, was making a high-pitched sound. So I was like, and I'd turn on the lights, and people would be like, turn it off! And I'm like, what? Like, I can't, it's a terrible sound. And I'm like, okay. And so that kept happening, so I went down to the custodial crew, and I'm like, I need a light that's to be fixed. They're like, what's wrong with it? I said, I guess it's making a terrible sound. So it turned out to be sort of a skit to get all the students to be able to, it was very clear to everybody else in the room, but none of the adults could hear it. So over time, that will start to kind of go down a little bit, that range. And again, there's not much reason that you need to hear that to that extent, but you obviously don't want to be damaging your hearing. So just sort of something to be mindful of, particularly as we're in, where so many of us rely on having stuff in our ears most of the time. So when we talk about sound, this is the range that we can hear. Sound travels at about 340 meters per second in air. So we'll say speed of sound equals 340 meters per second in air at room temperature. Because sound, so when we talk about light, that number will always be the same, always be the same, always be the same, as long as it's kind of traveling through a vacuum. But for us, we'll hear at about 340 meters per second. That changes by temperature. So depending on the, I think at 0 degrees Celsius, it travels at 331 meters per second. If you get higher than room temperature, you're up at 345, 346. So there's a range depending on the temperature of the air. Yeah?
Is this one of the reasons why it's quiet outside when it snows?
That's more because that creates this really soft blanket, and so the sound can't reflect. So like if I say something in it and I have a flat surface, it can echo back. And so just with all the sounds, there's that general kind of muffled echoing. We don't necessarily recognize it as such because you can't really have it stand out, but it's happening. And so when it snows and it puts all of that kind of soft coating over everything, it doesn't allow for any of that echoing, and so that quietness is there. I would also add probably fewer people are driving and stuff like that sort of thing, but yeah, it's definitely to do with the physics of what's happening as opposed just to the presence of something falling. Yeah?
So if a tree falls but there's no one around to hear it, is it still a sound?
Such a good question. Always a good question. If a tree falls and there's no one around to hear it, is there a sound? Well, technically, there is a disturbance of that air. So that energy is being transferred out in the way of sound. And it travels at a given frequency. And so the sound is present. But if nobody hears it, I don't know. It's just throwing it out. Yeah, this is a great question. I always like that one. So as things get warmer, it'll travel faster. So faster will be warmer, colder will be slower. I just think about it in the way of, if it's warmer out, I feel like I can actually function faster. If it's colder out, I feel like I'm like all rickety and stuff. So when we're making calculations, unless otherwise noted, we'll use 340. So if it's just as like, hey, this is happening and it doesn't give a speed, then we'll just keep it as that it's 340. Now, if it's in water, it's going to speed up. If it's through a solid, it's going to speed up. If it gives, sometimes it'll say that it's a hot summer day and therefore it's 346 meters per second. Fine. For our overall calculations of what we're doing, we'll use 340 meters per second. And so that helps us then to determine what's happening with the frequency and wavelength relationship. So if this stays constant, then as the frequency changes, the wavelength changes as well. So we can do a couple of practices with that, I'll take this part down. Still not used to this yet. So, things to think about with this. Let's take that range that we have and let's look at the way that would show up in the way of wavelength. So if we have, let's say our frequency equals 20 hertz. We know our speed of sound based on this equals 340 meters per second, and then we're going to solve for the wavelength here. So we know that V equals f lambda, and if we're solving for our lambda, we can rearrange that, divide both sides by f, so we have lambda equals v over f. We have our velocity, we have our frequency, so we have 340 meters per second divided by 20 hertz. 340 divided by 20 gives us a wavelength of 17 meters. So you think about that idea of the wave, and at our lowest frequency that's audible to the human ear, we've got a 17 meter wavelength. So it's a considerable size with that. Think about, like, if you've ever heard them talk about dog whistles. Dogs have a higher frequency threshold. So if you have a dog whistle, sometimes they do put some of that sound within the human range. Some of it is higher, super irritating to the dog, and like, okay, I'm coming. I'll get out of the bushes, whatever. So 17 meters is that longer wavelength. If we take and do the same thing here, and say frequency equals 20,000 hertz, and still velocity, that speed of sound stays the same. Rearrange in the same way, lambda equals question mark, so we can say lambda equals v over f. I'll step out in just a moment. We'll still take our 340, now we'll have 20,000. And so I'm going to get the zeros around if I don't calculate this. Let's see if this one works. There we go. So we'll go 340 divided by 20,000. We get 0.017 meters. So just under 2 centimeters, so about this long. So as we're looking at sound and we're looking at these calculations, a lot of the calculations will just go something like this, where we have still the same as we were doing before, where you have a wavelength and a frequency and get your velocity or any combination of these three variables to figure out the other. But then the other piece that we have with sound is this idea of what we hear in the way of a musical instrument. What do you hear when you pluck a guitar string? What do you hear when you play a wind instrument? How is that sound created, and what do we hear from there? So that's kind of the focus of what we'll be looking at mostly into next week, and that's called a standing wave. Standing wave happens when you have kind of, it's waves kind of adding up on top of each other in a really specific pattern. And I'll get into the details of that on Tuesday. Nope. I'll see you all on Monday. On Monday. Anyone need this still? Sorry, I'll step out just to give you a moment if you need to write anything down. Thinking. We have like 7 minutes left, so it's kind of that. See, this is where those 7 minutes that we had before. This is where the stuff would have ended before. gonna start talking just briefly about what happens with the standing wave. And then, on Monday when we're back in here, I have several more demonstrations. This is actually a standing wave demonstration. And then that's a standing wave demonstration. There's a few more that I have, and that'll help kind of drive us with what we're doing. So I'm gonna take this down and talk standing waves just for a moment. And then, and we'll see. How's everyone doing? Just like, I don't know, it's just such a different feel of what you're doing on a day. Everyone hanging in there? It's totally different? Okay. So here's what happens with waves. We know that if I send a wave pulse down this way, I just take it, I just like on a slinky and just like whoop, and I send a wave pulse and it's going that way. And if I have another wave pulse coming this way, when those two meet, they're gonna add up on top of each other. There's literally just gonna build up, so when they meet, in the middle here, if they meet, it'll be kind of twice as high, and then it would continue along the way. We saw that with that simulation that we did before break. We did the wave on the string simulation, and I had you send pulses at each other in different ways, and we saw it. They came together and they built up. If they were on the opposite side, this one's coming this way, this one's going that way. If they're on the opposite side and they meet, when they meet for that brief moment, they flatten out, and then they would continue along on their path. And so it's this idea that helps us set up for standing waves. Because what happens with a standing wave is you have these coming at each other repetitively in a very specific pattern that goes along with our frequency. And what that causes is it causes, as long as it's at the frequency that is going to be based on the structure of your item, so the way that the string is, or the length of the tube. And as long as it fits some specific criteria, you're going to create these areas that are built up on each other and areas that are still, and that's going to create the sound that you're going to hear. And that's the main basis what we're going to talk about in the way of a standing wave. So what does a standing wave sound like? Well, if you have these little like wobble, these little things here, you ever play with these as a kid? You can get different frequencies that are on there based on how you're spinning it. It's going to be the same every time. It's not a continual like whoop. You get some specific ones. If I go here, if I go faster, a little faster. Can I get faster? No, not really. This one is a different length, has a different sound. Okay, so depending on how that's set up, it will give you different types of sounds from each one of those. That's based on the way that it's going to build up and the way it's going to cancel out. So that'll create our standing waves, and when we start on Monday, I'll set up and draw out what a standing wave looks like. I'll show you some examples of what happens with that, and then there's some calculations that go along with that. This is where we'll bridge from what we know about how things sound from a physics standpoint to how they behave in the way of music, and why music can sound good and why music can sound terrible if you're not combining the right things. And so that's kind of where we're headed with that. So we'll go through that stuff on Tuesday. We'll get started on practice problems. And on Wednesday, there's a lab that we'll do with that I'll have set up here. It's one that I really like. It's one that is nice. It works well. It's nice and clear. And so we'll do that lab on Thursday, on the second time I see you next week. We'll take questions on practice problems then, and then you'll be off to do the rest of what you have. Any questions?